We can consider now some details of the implementation approaches to digital design. Of course, we can start with a basic design that is the so-called custom design, which means that every transistor is placed one by one on the circuit. So one actually designs the complete, let's say, electronic circuits transistor by transistor, and then puts every transistor into the design. That is called custom design. Then there are the other universe of possibilities. That is what is called semi-custom design. And it's semi-custom in the sense that part of the design is done by using things that have been already done, that are taken from a library, or that is done automatically or semi-automatically. And there are two large categories of types of semi-custom design, and one is the so-called cell-based semi-custom design. And the important part of cell-based semi-custom design is that the wafer is completely manufactured. So there's a complete fabrication of a circuit in each design. One is not using things that have been already fabricated. One can use cells that have been already designed, that can be directly put in terms of layout on the chip, but they have to be fabricated. Because there is also the other option of using parts that have been already fabricated. Then, so in the category of cell-based design, we have the two, let's say, subcategories that I discussed previously. Standard cells, in which the cells that have been already designed are relatively simple ones, such as logic gates or single registers or let's say something like that. Or the other possibility is to design with macrocells, in which one has relatively large blocks that are already designed. And the large block can be a memory array, but in some cases can be a complete small microprocessor to put on the whole chip. Let's say, for example, in some FPGA chips, there are small processors available that are put on the chip design as a single macro cell. And the other type of semi-custom design is the so-called array-based design. And the specific thing of the array-based design is that one does not need to do a complete manufacturing run. For example, in those cases, you can have a situation in which the front end has been already done. The front end is all the processing up to the complete fabrication of the transistors, and only the interconnections have to be put on top. So the chip is designed except for the interconnections, and you need to design and to fabricate only the interconnections between the different parts. This type of array-based design is called gate array. Okay? In the gate arrays, actually, the only part of the manufacturing that has to be done is the, let's say, the top interconnect layers, because also the bottom interconnect layers have been already placed. But the top interconnect layers can be placed in order to, let's say, design the complete circuits. So you have logic gates already fabricated, and then you need only to to, let's say, to tell the foundries how to interconnect them. The other option is the so-called reconfigurable logic, in which the hardware is already done. You don't have to touch anything, almost anything in the hardware, and you only can, let's say, reconfigure some logic. And there are, let's say, there is a spectrum in the type of reconfigurable logic that can use. You can reconfigure the logic in a way that is that can be changed, or in a way which can be done only once for the whole chip. And we are going to see the different possibilities. So, and this is the complete spectrum of semi-custom design. So, from standard cells down to FPGA cells, we call these four options semi-custom design. And of course, there are different degrees of flexibility and performance, in the sense that you have the higher flexibility with the reconfigurable logic, completely programmable, because you can change whatever you want every time with software. And on the other end of the spectrum, you have the standard cells, which have the highest performance. So you go to higher performance in that direction and to higher flexibility in the other direction. Okay? This is from the point of view of the performance flexibility trade-off. In terms of costs, it also you also need to consider that part, because of course the more you go towards the right, the more complex is the circuit, the larger is the circuit. So you typically, of course, because you have less efficiency by using large blocks, you have less efficiency because you typically have to use blocks only, also if you don't need every part of it. Okay? And then in addition to that, if you want reprogrammability, then you have, let's say, you have some overhead also in terms of circuits, and then on space on silicon. So you have larger areas and therefore higher recurring expenses. Okay, and if you remember, the recurring expenses increase super linearly with respect to the area. So you have a significant increase in that direction. On the other hand, you have higher non-recurring expenses when you go to standard cells. Because of course, for example, there are two types of non-recurring costs. The design costs, they are non-recurring, and of course it's a lot more complex to design with standard cells than with programmable logic, so the costs are higher. And of course, for example, with standard cells and with macrocells, you have to fabricate the complete wafer. With gate arrays, you only have to fabricate the top metal layers, so not the complete chip, so you have less costs from that point of view. And with the configurable logic, you practically have no fabrication costs. So the only cost you have with the FPGA is let's say the programming costs, the software programming costs. So this is important because the trade-off in terms of total cost of a single solution depends on the non-recurring expenses, on the recurring expenses, and also on the number of chips that you expect to sell. Okay, because of course, if you have larger number of chips, then you're interested in having small recurring expenses, so you tend to move in that direction. And if you have you expect to sell a very small number of chips, then you can have smaller costs if you move in this direction. Because in that case, you want to go away from the high non-recurring expenses. Okay? And this is actually, if I expect to sell, let's say, 10 million chips, it's very probable that I will go to standard cell solutions because I'm going to have a lower cost. If I plan to sell 100 different chips, then it's very likely that I go to FPGA solutions because at least I can, let's say, save all the non-recurring expenses. So, just to, let's say, summarize again, the performance flexibility issue trade-off is an important part of the important factor of the choice, and also the total size of the total number of chips that I expect to sell, because it matters a lot in establishing the cost of each particular solution. Okay, let's consider each solution in the detail. So we already discussed a bit custom design, a transistor by transistor design of a complete circuit. Of course, the advantage is high performance, and the main disadvantage is that it's time consuming, a lot of time to design a circuit, which has two implications. Of course, it's high cost, it's a non-recurring expense, but also it increases a lot the time to market. And this is an important factor for let's say, applications on which you expect a significant competition. Okay? High time to market means that, I mean, it can easily take a few years to design a complete chip, and sometimes you really cannot beat the competition in this way. So time to market is a consideration which is important. And so in practice, what happens? When this solution is used? Okay, for sure, independently of the cost, it is used for blocks that have to be used many times. So, for example, all the standard cells and the macrocells once have to be designed transistor by transistor with custom design. So the design of standard cells and of macrocells, the so-called library cells, is done with custom design. You also do custom design when you have a very large number of integrated circuits. And typically the integrated circuits that are sold in the largest numbers are microprocessors, especially the most, let's say, successful ones. And I would say also, at this point, FPGAs have large volumes. Okay? So the FPGAs are designed with custom design, and then they are used for, let's say, semi-custom design. And also the other situation in which they are used, which is more common than one can think of, is all the situations in which cost is not an issue, in the sense that performance is the most important parameter. You need to go fast, and then you need to, let's say, obtain and extract performance from any situation. And this is typical, for example, for defense applications. Traditionally, defense has been one of the main drivers of development and progress in electronics, because they have always been maybe less in recent years, but in the 80s and in the 1990s, especially during the Cold War, they were the only ones that really required huge performance without, let's say, thinking too much about cost. And so they were extremely good customers for semiconductor companies, because they could experiment new processes, new technologies with them. The other issue is supercomputing applications. And for example, since we just discussed before, also now let's say, hardware accelerators for machine learning are more and more done with custom design, because you really need to extract the highest possible performance from the circuit. So anyway, these are the situations. If you have, let's say, issues with cost and with time to market, then you need to go to another solution. In cell-based design, cell-based semi-custom design, of course, you remember the structure of the classification. Essentially, you need to have a library of cells that you want to deploy, to use in the circuit. And depending on the type, you can have different type of libraries. You can have standard cells, which means a library of simple cells. So logic circuits, or also MSI circuits. MSI circuits are circuits at medium scale of integrations, which means circuits with at most 100 transistors, such as a decoder, an encoder, a multiplexer. So relatively standard circuits that you need, might need in a digital circuit. And then you can have larger cells that are called macrocells, such as memory bank, or even mega cells if you have, let's say, PCI interface. That, of course, you can understand it's used in a lot of different circuits, or some are specific communication interface that is typically a block, a macrocell that, or a mega cell, but the specific names really depends on marketing more than on the actual thing, and that you can readily use, or even, as I mentioned before, a complete microprocessor that you want to put on a circuit. So how does the placement of single cell works? Just to understand, it's relatively easy. This is let's say, an image taken from a chip of the first generation of standard cells. And so this is basically the chip. Around the chip you can see the pads for all the contacts to the external pins of the circuit. And you see, basically, the circuit is arranged in rows. You have a row for cell, which is the black one. And then you have a row which is whitish, and it's basically, let's say, blank space used only to pass the interconnections. That you have another row of cells, and then another white row for interconnects. So the standard cells, the cells in the library, are done in a way in order to have a layout which is quite regular. Each cell has the same height and different width depending on the complexity of the cells, so that you can build a row together, as in that design, as a sort of let's say, Lego structure. You piece all the blocks one beside the other, side by side on a row, then on the other row, and then you decide what to connect to what. So each of those rectangles have the same height. Each of them is, for example, a different logic cell. And then you have that the input or the output are connected to the sides of the cell, and then the space in the middle is used to pass the interconnections. And this placement can be done manually, or can be done automatically, or can be done partially automatically and then adjusted manually, which is typically the situation that is most common. And as you can see, it's not extremely efficient in terms of density, because I mean, you see that all the white space is space on the chip, which costs because it increases the area of the die, but does not, let's say, provides a significant computing capability because there's only interconnections inside. Okay. But this is the typical situation in the 90s. Okay, so 20 years ago, a typical standard cell circuit was done like that. More recently, this is a new generation of standard cells. You can see the situation is much more dense, and again, it's not that different. All the cells are arranged in rows. All the cells have the same height. The only difference is that the interconnections are passed on top of the cells. They are not, you don't use, let's say, rows only for the interconnections. You pass the interconnections on top. So everything is much more compact and dense. And this is, let's say, doable because in the most recent technology processes you have many more layers of interconnects. So the lower layers can be used for the local interconnections within the single cells, and the upper layers can run on top of the logic circuits to let's say, connect the different logic gates without occupying additional space on silicon. So, and as you can see, this structure is a bit more regular than custom design, but still there's some, let's say, ad hoc structure because, of course, the different cells that you use in different places are different because of the different logic functions they perform. So they are very, they are only placed in regular positions and each cell is designed in order to have the same height so that they can occupy the total space in rows. Okay, how does one proceed in the design of a complete circuit, for example, with a standard cell solution? So the typical process is to start from a high level of abstraction and then to go down to the physical layer. Basically, in this way, one designs using a hardware description language the total complete chip even by using a behavioral description of the different blocks, so that one can have a code base that is able to map and to simulate completely the functionalities of the digital circuit. And then there are tools that help in passing from this high-level description to the physical layout of the circuits. And they are, let's say, classified in this way. One typically has the so-called logic synthesis tools that are able to take as input the hardware description of a logic circuit, the description in Verilog and VHDL, which are the languages for hardware description of the circuits, and to translate them into a design at the gate level. So in a circuit consisting of logic gates. This can be done practically in a totally automatic way. It's a sort of software compiler. Okay? So from a high-level description into a level into a description at the level of single gates. So this process is not always, let's say, extremely efficient. Because sometimes the gate level design resulting in this way is less efficient and more complex than what one would obtain by designing directly at the gate by gate the logic circuits. but of course it is faster. So it's exactly like programming at a high level, programming a software with a high abstraction level compiler, and then high abstraction level language, and then compiling it into let's say lower level language. You lose efficiency, you lose let's say quality of the code, you lose performance, but you gain a lot in design time. Okay. Once you have the gate level design, what you need to do is to obtain the layout. So for each gate, you can go to the standard cell, and you know to which other gates that gate is connected to, and then you can place the cells on the layout on the area of the chip, and then place the interconnections. And this is typically also automated with the so-called placement and routing tools, which let's say know the problem and organize the positioning of the different standard cells in order to, let's say, optimize the space, minimize the total length of the interconnections, and so on. And this is something that can be done automatically or in a quasi-automatic way by checking again and optimizing the situation. And at the end, by using displacement and routing tools, one can obtain a standard cell layout. So the possibilities are from a standard cell layout, one automatically has the layout that can go to Foundry. Okay. So this is the sequence. Of course, one can directly do by hand the standard cell layout, or can do by hand a design at the gate level and then use the placement and routing tools in order to, let's say, accelerate the definition of the layout, or can go to the design in terms of a hardware description language and then use these semi-automatic tools. Again, there's a typical trade-off between design time and performance that you observe with software programming. The design time is faster if you start with a higher level of abstraction description and then you go down, but of course you typically obtain a poorer performance by using a hardware description language. Okay. One thing that I think it is important to mention is that this fact, this organization of the work and of the different layers of abstractions is very suitable to the what has become the most common business model in the semiconductor industry, which is the fabless model, in different ways. Because, for example, one can do the total design of the chip in one company, then at the end one can have the so-called GDS files, which are the layout files of the chip, send them to a foundry, which is going to fabricate them, and return the chip back to the designers. And this is a clear split in the work required for a chip. The designers in a company, and then the technologists and the people responsible for fabrication in another company, which is called the foundry. This is the one type of split that one can have. But what happens is that sometimes the foundry also provides already the standard cells. So one can actually, let's say, split the role of the designers and the role of the foundry in this place. For example, that the designers can arrive up to a gate level design and then send all the gate level design to the foundry, which has its own library of standard cells, and go from there to the implementation directly. So this let's say, segmentation of the different levels of design is quite suitable to the fabless business model. And let's look at the different actors that one can have, because many more actors can come into place, and they are quite common in the most recent years. So one actor is the fabless company, as I mentioned before. So the fabless company does the design, then sends everything to the foundry, gets back the chips, typically tests them inside the company, and then sells them. Okay? There are many large companies now that are practically fabless. The largest one of those are, maybe the largest one is Qualcomm, which is the company that is probably making now most of the revenues from the Snapdragon processors for all the Android phones. Then, for example, Marvell and Alloy Semiconductor are companies that are specialized in chips for telecommunications in the case of Marvell, or for power management in the case of Dialog, and they are chipless ones. So they design chips and sell chips, but they are fabricated elsewhere. And also other important fabless company are the FPGA companies. Typically, the FPGA companies are only designing and selling the FPGAs, so Xilinx and Altera, the largest ones, but they fabricate them at external foundries. And they are very good customers because they have very large volumes, and they are typically the first customers for a new process because they have extremely large volumes. So, on the other hand, you have the foundry. The foundry typically provides fabrication, and as I just mentioned, they very often also provide standard cells, ready-made standard cells for fabless. So they can really accept a design at the gate level, or even at the standard cell level, but without, let's say, without providing the library, the complete library to the designers, but only let's say, the external shape of the standard cells. And this is what they say: good made standard cells and the fabrication services. And as I already mentioned, these foundries are mainly in the Far East, Taiwan and South Korea. There are some fabless, there are some foundries also in Europe and in the US, but most of the business is in the Far East. And in this model, you also have IP vendors, the last line here. And the IP vendors are companies that only sell, in this model, it works also if a company only sells the macrocells. They can sell just the macrocells that, let's say, a fabless company can put in the design. And there are relatively huge companies which thrive on that. For example, ARM, which is a relatively large company. It was bought by SoftBank for 30 billion, so that is the size, but it's, the 30 billion is not a small company. And they only sell the IP of the processors. So they sell typically the IP at the gate level of some generations of some architecture of ARM that, for example, is used by Qualcomm for making, let's say, smartphone processor. Okay. They take at the gate level description typically of the chip by ARM and use it as a library cell in the design of their processor. You can see that this way of proceeding, of course, can accelerate a lot the design time. ARM is a specific example. It's quite extreme, I would say. But there are companies, for example, that are specialized in let's say, memory banks, that sell IP for memory banks so that other companies can buy the library and include those, for example, special type of multi-access memories directly in their chip. And this type of IP vendor can work at the gate level, but can also work at the level of the macrocell, just by, which means selling a specific IP for a specific technology, okay, for a specific CMOS technology. So there are different business models for that. And I would say that this is the typical situation that you have now. So you really have companies that really provide only macrocells to other companies, and companies specialized in fabrications, and companies that put everything together in the design of a complete chip. So you don't need to think of design in terms of 3 people working around the table to design a microprocessor. Okay. Of course, there is also the other option, which was the most common once, that is now also present, in any case, even if it's not the typical situation, the situation of the so-called IDM, the integrated device manufacturer, which is a company that does everything inside. So it does design, then the fabrication, then the testing, and also the sales. And the largest one of this block is Intel, from the point of view of circuits, of integrated circuits. But also Samsung does the same thing. Also ST Microelectronics does the same thing, and NXP and Infineon, the traditional large semiconductor companies, still have important foundry capabilities inside, and therefore can also fabricate their own chips. But now, of course, the things are changing, because all the three companies, Intel, Samsung, and STM, also offer their foundries as a foundry service for other companies. So things are significantly mixing up. Okay. Regarding the macrocells and the macromodules, the large cells, there is an important distinction to be made between so-called hard and soft macrocells. Because, let's say, one possibility is to design a macrocell down to the layout level, so a macrocell which is designed for a specific CMOS process. Okay? So, which means that you have the functionality that is predetermined, but not only the functionality, also the physical implementation, which means that you can really, let's say, once also the physical implementation is predetermined, it means that the performance is typically maximized for that standard cells, but of course for that macrocells, but of course that macrocells can only be used with one specific CMOS fabrication technology. And this is, let's say, quite typical for memory. I would say it's the only solution for memory, and it's often used for embedded microprocessors, not only used for embedded micro. No, it's not the only solution for embedded microprocessors, but if you want to, let's say, maximize the performance of microprocessor which is sold as a macrocell, you need to custom design it for a specific CMOS process. The other option is to sell a macrocell which is portable to different CMOS processes. And what it means is that what you sell is the gate netlist of the macrocell, and then the implementation from the gate netlist to the standard cells is done depending on the specific CMOS technology used for the implementation. So you sell the macrocell at a higher level of abstraction, and of course the functionality is predetermined, but the physical implementation is not predetermined, because the transition from the macrocell to implementation in standard cells still has to be done. Okay? And this is typically is the situation that is most common for the IP vendors that I mentioned before. Because typically an IP vendor, for an IP vendor it is easier to sell a macrocell that can be used for all CMOS processes than to optimize the same macrocell for many different possible foundry processes. And therefore that is much more common. Of course, this solution is more convenient, but it provides a lower performance with respect to the ones that is in principle obtainable. It's even less expensive in practice to buy. But it's important to note that there are two possible different solutions. So, for example, one macro module is this one. This is an SRAM, an 8 kilobit SRAM. You see the structure, of course, it is a memory, so the structure it's very regular. You need an 8 kilobit SRAM, you take it from the library and you put it directly into the design, and it works. So, yeah, you typically also have a bit of programmability in the library, in the sense that you can specify the size of the RAM, and it has an algorithm inside to build the RAM according to specifications. And then you can have some let's say, other macro modules that are less regular because they are internally custom designed and, for example, perform some logic functions and are used for the specific applications. Okay. So, just to summarize this just block diagram of the design flow for semi-custom design. Let's try to follow it completely. So, in the case of semi-custom design, of course, it's useful to, let's say, separate the design into phases. One phase for the functional implementation, so the implementation of the function of the circuit, and one for the physical implementation, from the function to the physical layout of the chip. And of course, in the process, one can use the design tools that we have already mentioned. So what one does is starting, let me just, yeah. Starting from the design capture phase, the phase in which one, let's say, designs the circuit at the, let's say, specific decided level of abstraction. So at the design capture phase, one can use a schematic, or one can use VHDL, or one can use a mix of VHDL for some blocks and directly schematic, an electrical circuit schematic for other blocks. And in that phase, one can use large IP blocks from taken from a library. So, starting from that, one can one can use a logic synthesis tool and transform the initial design into a gate netlist with some placement and routing constraints. So let me let's say specify what a placement and routing constraint means. In this logic synthesis phase, and for example in the VHDL description, for each block, one typically needs to specify also the typical delay of the block. The delay according to which the outputs change as a function of the change in the input, for example. And from a physical point of view, this depends a lot, for example, on the distance between one logic block to the other logic block to which the signal needs to go. For example, I can assume a certain delay in the signal from one logic block to the other, and this delay that I have assumed, of course, puts a constraint on the distance between the two blocks, because the more distant the two blocks, the larger delay I probably need to have. So when I put some constraint in or make some assumptions in the delay of the signal in the VHDL circuit, implicitly I'm putting some constraint in the distance between two logic blocks. And this has to be verified when I go to the physical layout of the circuit. Okay? So the logic synthesis tool performs the, let's say, the transformation of the design from VHDL plus IP blocks to a gate netlist, and it annotates the netlist with some constraints on the placement and routing. And there are specifically constraints about the distance of the interconnection. This is going to be used later on. Then from when I have the gate netlist, I can simulate the total circuit at the gate level and check if the function of the circuit is what is expected from specifications. So at this point, after the logic synthesis, I can perform some simulation of the circuit. For example, provide some input stimulus and verify if the outputs are what I expect, and then check if the operation is correct. This is what is called a pre-layout simulation and verification. It's called pre-layout because I do not have a physical layout. I'm doing it on a logical circuit, on a circuit at the gate level. Okay, this test has to pass, because if it's not passed, then I need to go back to the design capture phase to adjust the VHDL or the use of the IP block because something is going wrong. Okay, so there's this design cycle at the functional implementation level, which only finishes when, in pre-layout simulation, the circuit behaves as it needs. Okay? After this phase is successfully completed, we can go to the physical implementation phase, which means that we have a good circuit at the gate level, and we need to obtain a physical circuit. And so what do we do? First we do a phase which is called floor planning, which means that we put on the floor all the logic gates that are required. We put and we position them according to our needs. So the first phase of floor planning is mainly a very rough design, very rough initial design, in which I can decide the total area of the chip, because when I know the size of the gates, which gates I need, I can more or less have an idea of the total area of the chip, of the input and output path that I need. So I have, let's say, the frame of the circuit. And then there is the phase of placement and routing, in which the logic gates are individually placed and interconnected. And it is in this phase that I need to verify the placement and routing constraints. So the placement and routing needs to be done by taking into account the constraints from the previous phase, because those constraints are needed in order to ensure the timing constraints of the circuit. Okay. This placement and routing can be, of course, helped by software tools. And in the end, what I have at the end of the placement and routing is the total layout of the circuits and the set of masks that I need to fabricate the circuits. Okay? Now, once I have the layout, I need to, in principle, I could go to the foundry and verify the actual physical circuits. But this is going to be costly, because if it's not working, I spent a lot of time and a lot of money to build, to fabricate the circuits without having, let's say, nothing working in return. So what is typically done is a post-layout simulation. So from the layout, there is a software tools which makes the electrical circuit extraction. So from the layout, this tool recognizes the different transistors and the different components, rebuilds again the electrical circuits, so that one can simulate the circuit with the circuit simulator such as Pisa. So one can perform a simulation of the circuit extracted from the layout. And this is called the post-layout simulation. So this is very important, because the extractor does not know what is the initial circuit that has been designed. So it's an independent verification of the circuit. So it extracts the electrical circuit, and then you can simulate. If it works, at this point you send the masks to the foundry. If it's not working, you go back and try to debug everything to understand where the error is. Okay? So there are these two different phases, and they are quite important. Of course, I must say that this post-layout verification is only possible if the circuit is not too complicated, because otherwise it's really not doable. So it's done, for example, it's very often done for communication circuits, because they typically push the technology to high performance, and it's important to verify if physically this can be obtained. But for example, for large microprocessors, it's very hard to do it for the whole chip. So what one typically does is the post-layout simulations of only the most critical part of the circuits, or all the total circuits, because it's extremely expensive. A microprocessor can easily have 1 billion transistors, and of course, if you need to simulate electrically a circuit with 1 million transistors, then it's not really doable. Okay. But the design flow is is this one. Okay, let me consider now the other part, which is the array-based implementation, the part which does not require complete manufacturing. So, you remember there were two different possibilities, the gate array and the field programmable gate array. As I mentioned, in the gate array, you have that the front end, so the single transistors have been already fabricated. You start with a wafer in which already the single transistors have fabricated. You only need to put the interconnection layers, the metal layers on top. And for this reason, you only have to design and then to fabricate the masks for the interconnection layers on top, and then to do only that part of fabrication. For the field programmable gate array, instead you don't touch anything from a physical point of view. You have a no, it's not wrong. You don't touch anything from the physical point of view in the foundry. So basically, the chips are shipped from the foundry in a complete way. They are all equal when they are sent to the users. And then, so there's a total separation between the manufacturing phase in the foundry and the implementation phase, the phase in which you use the FPGA, and then you need to program the FPGA. I was saying that you don't do anything physically, but this is not totally true, because sometimes in the implementation phase you can physically change the FPGA, and we are going to see how. And just to stress something that I already mentioned, the advantage of FPGA is that in the manufacturing phase you have large volumes because they are all equal. They're large blocks or equal and sent in millions of samples. And this means that the non-recurring costs are low because the denominator is very large. And also the other part is that you don't have to pass from the foundry, and therefore don't pass from the foundry, and therefore the time to market can be very fast. You only have to buy the FPGA and just implement it, program it. You lose something in performance, and the recurring cost can be high because, for example, a single FPGA can easily cost a few $100 each. So it's not really, they're not really cheap in terms of unit costs. So how are the cells programmed? This is, there are many different possibilities, and that are, let's say, all used in the market. One possibility is the so-called fuse-based FPGA. So in the FPGA, what you have is an array of logic circuits that can be, let's say, programmed, or for which the interconnections can be programmed in order to, let's say, implement different functionalities. Of course, the details of what is programmed is, let's say, controlled by a software tool which is analogous to a compiler, which basically starts from the logic description of what do you need the FPGA to do, and then accordingly uses the logic that is available. But the way in which the programming occurs can be quite different. One situation is the so-called fuse-based. In the fuse-based, typically you have a write once option, in the sense that there are some interconnections that can be opened once, or that can be shortened once. For example, in the case of the fuse, you have a short circuit, so an interconnection that is present, and that can be interrupted. For example, you have the analogous of a fuse, of un fusibile. This is a short circuit, you have interconnections between these two blocks, but if you have a large enough current through the interconnections, then the temperature of the narrow part of the interconnection rises a lot, rises above the temperature at which the fuse blows up, and therefore the interconnection is in high impedance mode, is open. Okay, and of course, once you do it, it's forever, and it can completely change. It changes the configuration of the circuit. And you have also the opposite part, which corresponds to the antifuse situation, and which is illustrated there. You see there are two layers of conductors that are typically polysilicon that are at fabrication separated by a thin layer of insulator, and so they are insulated at the beginning. This ono dielectric is an oxide, nitride oxide dielectric. So the electric is, of course, an insulator. But by applying a large voltage between the two conductors, you can break the insulator and then put the two conductors in contact, so that you can program the contact. And of course, this is, again, not reversible. This is done once forever. You do it at the beginning. Typically, you have to put the FPGA on a board which is used to program the FPGA, and then you don't need to know which exactly interconnections have to be closed or opened. Typically, there's a software tool which is provided you by the vendor of the FPGA, which starts from the VHDL or the gate level description of the FPGA and translates it into a set of contacts that have to be opened or closed. Okay. And this is it's quite common, but there are also other possibilities which are reversible, and they are based on some memories which control the interconnections. And they can be non-volatile memories that control the interconnections, that can be a sort of ROM or PROM that can be programmed, so that you can change the status of, for example, of a pass transistor, which is interconnecting to different regions of to different blocks, for example. Or you can have the same thing but controlled by an SRAM, so a non-volatile, a volatile memory, a static memory, which means that basically at the boot of the FPGA, that there's a phase during which the status of each SRAM cell is read from an external ROM, and then the SRAM is written, and then you can start the operation. So basically, this is also quite common, because to have an SRAM-based FPGA, you need a standard CMOS process. For the other case, you need a non-volatile memory on board of the CMOS process, which is a special CMOS process. For the fuse-based, you need a special fuse-based technology on the process. In this case, you have a let's say, standard CMOS process, of course, there is a disadvantage that and before starting the FPGA, you have to boot it every time. Because essentially you have to program it at boot every time. So let me just check. I'm close to finish, so I'm continuing instead of making a break so that we finish early. As I mentioned, basically the only option is to close and open a contact or to pre-program a memory, to program a memory. So how does this translate into programming the logic? Okay. There are two easy situations that you have probably already seen. For example, the array-based programmable logic, the so-called PLA or the PAL, it actually works by opening and closing a contact. Because, for example, in the case of a PLA, you have an AND array and an OR array. And you see, in the AND array, you have, in this particular case, you have 3 inputs and 2 outputs and 3 word lines. I mean, this is just an example. Of course, you can have a much larger array. And you see, you typically have, for each word, you have a tree.
Scusa, ti posso interrompere 5 minuti? Proprio 5 minuti?
Sì.
Per mostrare l'aula questo segnale.
Prego.
Era questo come avevo dato. È un po' complicatissimo. Sì. Sulla parte più alta. Sì, infatti stavo considerando questo è più semplice. Questo però è bello.
So, you see what is the situation. Basically, you have a 3 input AND, and the input is connected to C and not C, B and not B, A and not B. So actually what you can do is specifying the AND plane by opening or closing those contacts. Okay? And the same, I mean, there are some possibilities in which you can do this on the AND array and not on the OR array, or you can do it only on the OR array, or you can do it both on the AND and on the OR. And essentially by defining where you have the contact and where you don't have the contact, you can implement any combinatorial logic, any OR of AND logic function. So, and this of course is easily done with fuse or an anti-fuse technology, and this is what is typically done. Of course, by writing an SRAM, you can also specify a lookup table, so implement any combinatorial logic. For example, in this case, if I want to implement this specific logic function, in this example I have 2 inputs and 2 inputs and 1 output. So let's assume that this is the input 1 and the input 2. I only need to write 0, 1, 1, 0 here for the different, if this is selected with 0, 0, this is with 0, 1, this is with 1, 0, and this is with 1, 1. And of course, depending on what I write in the memory, I'm specifying the lookup table that I want. Okay? And again, this is doable with a non-volatile memory or with an SRAM. So these are the 2 typical situations. Not the only ones, but they are, let's say, easy to grasp. Okay, and just to just to finish this part by illustrating two things. For the sea of gates, this is the situation that you have. The sea of gates is a gate array in which the single transistor and the position of the lower interconnections is done one for all, and you only have to specify the top metal interconnections. And you see that basically, I mean, the picture is quite evident. You have some, in this case, you have a regular part in the lower left region because there is a memory subsystem there, and therefore everything is extremely regular, also in terms of interconnections. And then the rest, in which you have the logic, you see this very random, apparently random interconnections, because you basically had to interconnect pieces of logic that were already there. Okay? So, of course, this part is, let's say, from the fabrication point of view, is relatively easy, because the fabrication of the metal interconnection is done at lower temperature, and it's much less expensive than the fabrication of the lower levels. So it is actually, let's say, something that requires some fabrication steps, but is much less expensive than the complete fabrication of the chip. And this is, just to have a pictorial view, the image of an FPGA with SRAM programming by Xilinx in this case. So you can see the structure is extremely regular. Each of those squares are, let's say, small processing elements containing some pieces of logic, some pieces of memory, interconnected together, and then, of course, you need a compiler that can translate the high-level description or the gate-level description of the circuits into the specific programming of all the SRAMs in all the blocks in order to build the corresponding circuits. But this part is something that you are looking with in detail with Professor Fanucci. Okay. I'm stopping here for this part, and that's it.